Good morning, everyone. I'd like to welcome you to today's installment of the Royal Ontario Museum Speaker Series, which is sponsored by our Museums Cooperating Society. And as always, we're really grateful for their support for this and the other initiatives that they help us with. So today we're going to not have a talk about dinosaurs. I'm very excited about that. Nick Cairns, who's the new curator at the Royal Alberta Museum he's the curator of non-avian vertebrates. So in other words, fish, amphibians, reptiles, and mammals. And Nick just started there last June, so he's hasn't even hit his first year anniversary, and very happy to have him here at the museum. So Nick is a herpetologist, and he's worked on frogs, turtles, snakes, and lizards across Canada, the US, and Australia. His particular interests in his new role at the RAM are the amphibians and reptiles of the Palliser Triangle, their biogeography, genetic connectivity, and ecology. And Nick's also bringing some ongoing projects with him to the RAM, including investigations into the relationship between snow and horned lizard overwintering, as well as niche divergence in skinks. And outside of his work, Nick and his wife are working to raise a couple little naturalists on the prairies. So today's talk is Forests, Prairies, Puddles, and Badlands, exploring Alberta's amphibians and reptiles. Would you join me in welcoming Nick?
Thank you very much for the introduction. All right. So yeah, today we're going to talk about reptiles and amphibians of Alberta. We're going to talk a little bit about their diversity, about their biogeography, and about their life histories. So first off, I will give another introduction because I appreciate Jim's introduction, but I already have made this slide, so there's more pictures of me. This is far more in my natural attire. As a field biologist, I'm feeling rather constrained in my suit today, but you got to make use of it sometimes. I am raised on the West Coast, and then I moved to Manitoba when I was 17. I did my undergraduate degree in Brandon, Manitoba, looking at habitat suitability modeling and ecology of prairie skinks, as well as red belly and smooth green snakes. I then went to Ottawa. I worked at the University of Ottawa and at Carleton, where I did a master's degree on fisheries biology and turtles, essentially bycatch in turtles. So that was more of an engineering project than a turtle biology project, but we had a lot of fun and found some neat things about turtles as well. And then I did my PhD at Queen's in Kingston, and I was looking at the phylogenomics of spring peepers, which are a pseudacorus tree frog, so somewhat tree-ish tree frog, but primarily on the ground sort of tree frog, all across their range in eastern North America. And then I came home to my beloved prairies, where I live in Val Marie, Saskatchewan. I worked at Grasslands National Park before this as an ecologist and as their reptile specialist. And I also work with COSEWIC looking at modern conservation. So I have a lot of fun with these different groups. As Jim mentioned, my interests are primarily arid herpetology or semi-arid herpetology with a smattering of overwintering ecology, because we are, after all, in Canada, and if you're looking at an area with as low diversity as Canadian reptiles and amphibians, you might as well look at what they do in the winter. I also do some phylogeography, and throughout my career, lizards have been a constant. But overall, I think you could describe me as a herpetologist. So what is herpetology? It's an area really defined by the taxa that you study, as opposed to the sub that you study. So it's not like ecology in that we're looking at the interactions between different species. It's that we're looking at the species themselves. And there's all sorts of ways you can split herpetology. But overall, it's the study of reptiles and amphibians. And that in and of itself is actually a bit of a problem, because reptiles and amphibians are not really that similar. In fact, they're probably more different than they are similar. So what are they? The way that we can best describe them is ectothermic tetrapods. That's basically where we get to. They take heat from the environment to do most of their physiological processes, and they, for the most part, have a common ancestor with 4 legs. And that's about as tight as we can get with this grouping. And the reason that they are grouped is primarily because of Carolus Linnaeus. Old Carl just didn't seem to care all that much about these things and just kind of lumps them together because he was busy making diverse groups of mammals. So when we look at what Carl did in the 1750s, this was his definition of what a reptile and an amphibian was. These are foul and loathsome animals, abhorrent because of their cold body, pale color, cartilaginous skeletons, filthy skin, fierce aspect, calculating eye, offensive smell, harsh voice, squalid habitation, terrible venom, and so their creator has seen fit to not exert his powers to make more of them. And so you can tell that Carl was not a huge fan. And so he just didn't bother to look too deeply into any of these things, because we could make a whole hour-long talk about how Linnaeus was wrong about most of these aspects of this paragraph. This paragraph is an hour dissecting in and of itself. But we can move on from Carl, or we can move on in 1 second, because that last point about their creator not making many of them is totally off base. And that's the only, we're gonna move on from Linnaeus after this, but there are roughly 8,000 species of extant amphibians, and that's a very conservative estimate. There are more species of amphibians being found every year. I'm currently describing a new species from the United States. So if we're still finding new species in the United States, we haven't really reached peak diversity with amphibians. This diversity is split into 3 orders. The most populous one, or the most speciose one, is the frogs. Probably most of you in the room are familiar with frogs. Small 4-legged hoppy creatures, not much of a tail as an adult. You've probably all seen a frog, Kermit at least. Then you have the salamanders, which are fairly similar in morphology, except for they're a bit stretched out. They've got a tail, and their heads are a little bit more garbage can liddy, from my experience. And then the last group is one that we don't have in Canada. They're located across the world's tropical regions, but the Sicilians are a really neat group. They're not particularly speciose, 100 to a couple hundred species, but they have an immense amount of life history diversity and trait diversity. So they're a really neat group that I suggest everyone look at. They mostly look like earthworms or eels, but they're very cool to look at. Definitely worth looking at. Some of them actually feed their own offspring on milk-like substance located in their skin, which their offspring actually rip off of them and eat them. So they have maternal cannibalism. It's a very cool group. So please look them up. They're very neat, but you won't see one in Canada, unfortunately. The other thing about amphibians, and the only generalization that you can really make, is that they are relatively tied to moisture. And even that, you might not be able to say wholly. For the most part, the life history of amphibians have egg and larval stages that involve water in some way. Some have bypassed it to some extent, but they all need water at some point in their life, a little bit more than other groups of terrestrial vertebrates need water. The other thing about amphibians is the fact that I just said that made me wrong, because there's always an exception with amphibians. They're so diverse, they're so old, so interesting, and they found all sorts of ways to make livings in some of the most harsh conditions. So despite the fact they're tied to water, they're not all tied that tightly to water. I missed a point earlier. We'll move on to reptiles, though. Reptiles are even more speciose. There's conservatively 11,000 species of reptiles. These are just 2 examples. There's a prairie skink from Manitoba with her eggs, and a Microides coral snake from Arizona. They are a really interesting group as well. They're more speciose, and they're split into 4 extant orders. And there's an asterisk there, and we'll get to that in a second. The first extant order that we're going to talk about is the lizards. Lizards are near and dear to me, the squamates. Now, when you hear squamates, people often say lizards and snakes. The problem with that is snakes are just lizards. Snakes are just one of many radiations of lizards that have reduced or absent limbs. In fact, most snakes still have some form of pelvic girdle and limb. So most radiations of snake, not most species. So there's actually 27 cases within lizards where limblessness or limb reduction have occurred, separate occasions. The next group is quite close to squamata, and that's the rhynchocephalians, the tuateras. We have very few rhynchocephalians. They used to be quite common in places, but we're pretty much down to the tuateras of New Zealand now in rhynchocephalians. They look a lot like lizards, but there's some major key factors that they differ from. For example, they don't have external genitalia that they can evert, whereas all of the squamates do. So they breed more like birds with exchange across cloacas. Next we have turtles, and their placement is a little bit more controversial because some people had historically put them closer to squamata, and some people had put them closer to the crocodilians. Most recent genetic evidence suggests they're sort of towards the archosaur crocodilian side of that base, but I'm sure there's people in this audience that know a lot better about that sort of thing than I do, so I'm going to stop talking before I get called out. But the next group is the archosaurs. And the reason I put archosaurs is because our definition of reptile as the way that I've described it also includes birds and dinosaurs, which most people don't really have a huge issue with, but ornithology, as you can tell by my non-avian vertebrate status at the Royal Alberta Museum, most people don't necessarily clump birds with reptiles, at least in practice. So what sort of connects these groups? And that's largely the fact that they're relatively free from water. The reptiles developed nice, dry, water-resistant skin, so they were not as restricted to staying near water as amphibians. And they were also one of the first groups to have these fancy extraembryonic membranes to protect their embryos in development and allowed for eggs that could be laid on land. So they have the amnion, so if everyone's familiar with amniotic sacs in humans and all other sort of amniotic vertebrates, these ones also have amnions. They also have the chorion and the allotois, which provide respiration and waste exchange, respectively. So what this meant is that these animals could take the water with them and then invade land more effectively than amphibians could. So let's talk about Alberta. Alberta has quite a few herps, enough herps to keep me interested. And when I say herps, that's just my abbreviation for reptiles and amphibians, herpetology, the creeping things of organismal biology, vertebrate biology. This is just sort of a heat map that I made by layering all the Alberta Conservation Association's range maps in Alberta. And you can kind of see a neat pattern. The numbers on the top and bottom point to the richness at those sites. So our highest richness site for amphibians has about 5 species that are sympatric and 2 up in that northeastern corner. And for the reptiles, right down in the southeastern corner, we have about 8 species, and 1, the indomitable red-sided garter snake that makes it all the way up into the Northwest Territories. Now you can see that most of these animals come near or reach their northern range limit in Alberta. And Alberta actually is a relatively low richness province, largely stemming from the fact that we have a relatively small southern base. But BC, for example, has 34 species of reptiles and amphibians, 20 amphibians, 14 reptiles. And Saskatchewan has 21, 9 amphibians and 12 reptiles. So you can kind of see there's some interesting placement. So let's get into why those animals are where they are. The first thing you need to understand about exothermic organisms is they're very much tied to the conditions around them because they're reliant on those for all their physiological processes. And then, as we've mentioned, amphibians are often very tied to moisture. You can see here the basic patterns of mean temperature. We've got nice high temperatures here in the south, and it gets cooler. You got relatively low precipitation here in the edge of Palliser's Triangle, and then it gets more wet as you get closer to the mountains and sort of in the center and up towards areas where we have a little bit more tree growth. So this region here is sort of the beginning of the parkland where we start getting into more trees. And there's a bit more moisture there. And those abiotic conditions, so the temperature, the humidity, the soil types, all figure into the biotic community that exists in those regions. And amphibians and reptiles are part of their biotic communities. They rely on other animals for prey. They rely on trees, for example, providing cover and access to subsurface cover. And you can see here the basic outlay. We have our nice dry prairie, and then a fescue prairies, and then we get into parkland, and then it gets more and more boreally as we get higher up. And so species that might exist in the montane forests of the mountain edges, something like a long-toed salamander, would do great out there. It's nice and wet, but it's quite cool. Whereas a racer or a horn lizard is definitely in these areas where they can thermoregulate a little more easily. There's less cover, there's less moisture, they can get nice and hot, which is what they need. The other thing that restricts where animals are found in Alberta is the fact that this whole province was wiped clean of any reptile or amphibian. And up until about 12,000 years ago, this is a rough estimation, or not a rough estimation, a pretty good estimation of what the ice cover was and proglacial lake cover was at about 12,000 years ago. You can see that southern Alberta, you could start to invade at about this time if you were relatively cold tolerant. But there was no reptiles and amphibians left here, even though there was a few areas that were unglaciated, like the Cypress Hills. There wasn't very many good spots for a reptile or amphibian. So everything we have here came from further south, so they had to be able to get there. And some of them are very restricted in habitats. So a lot of our species are sand-loving species. They're not going to live in hard pan, dry soil as well as they do in sandhills. But they can't get to all those sandhills because not all of them are connected. So they had to wait for the glaciers to recede and then leave giant piles of sand, which are, of course, sorted by the wind. And so we have these different sand piles, like the Great Sandhills in eastern Saskatchewan or the Athabasca Sandhills. In the Great Sandhills and in the sandhills of southeastern Alberta, there's lots of diversity of reptiles and amphibians. But when you get to the Athabasca Sandhills, due to temperature and the inability to get there, there's less reptiles and amphibians, almost none. The other thing is access is dictated in some places by degree days and rivers. River coulees, like you can see here, are excellent thoroughfares for reptiles and amphibians and other animals. And so drainages are often really important, not just for aquatic species, but for non-aquatic species too. In fact, a number of our species live, this is a drainage map of Alberta, a number of our reptile species just exist in the Milk River. So in terms of native distributions of racers and native distributions of painted turtles, it's just in the Milk River drainage. So it's a really just a little tiny edge of the province. And so you can see here, when we look back at these maps, why these animals are here. There's a mixture of it's too hot and dry, but this is just right for those species that can handle a bit of the colder temperatures as well as a bit of the drier temperatures or drier conditions. And so at the edge, in the sandhills, at the edge of the parkland, all of a sudden we get a lot more reptile, or a lot more of amphibians. And then that access and that heat, which is what they really need, as well as probably overwintering conditions, limit reptiles to the southeastern corner for the most part, except for the most generalized of all the snakes, the indomitable red-sided garter snake. The other aspect about these conditions is they have to exist at the right time. Seasonality is incredibly important. If we had a whole bunch of rain or snow in the middle of winter when it's too cold for these animals to use it, they can't use it. So they can't exist if your season is at the wrong time. Timely rain events and timely flooding events are really important for these dryland species. This is a western tiger salamander. They won't move unless the ground is damp. At least they don't move very far. And so if they want to get to a breeding pond, not only does the breeding pond have to be full, but it has to have rained so that they can move those distances without drying themselves out. The other element of it, and that's probably another talk, is the importance of snow when snow comes and how it relates to temperature. If it's too cold before the snow comes to insulate, those animals might die over winter, because there are species that are quite freeze tolerant. But if they don't have some insulation, they're not going to survive. But let's get into life histories, because it's fun. Every one of our amphibians in Alberta starts its life as an egg. These are leopard frog eggs. These are chorus frog eggs. You can see they live in a jelly membrane. They'll stay there for a while and eventually hatch, squiggle out as little tadpoles, and begin feeding as much as they possibly can, because they don't often have very long to metamorph in Alberta. Reptiles, most of our reptiles also lay eggs. This is an example here. This is the only known yellow-bellied racer nesting site in Canada. This one's in Saskatchewan. I'm sure there are more. We just haven't found them, and it's probably best that we haven't. But you can see that it might be quite limiting. There's lots of individuals using this nest. There's also multiple species using this nest because it's such a special spot. Having the right conditions, even though they're free of water, it still needs some humidity and they still need the right temperatures, because we're living in a very confined thermal gradient in southern Alberta. These animals have found a little sand pile on top of a very clay-based hill. This is the only sort of gravelly sand within a couple hundred meters, and they found it, and this is revisited every year. It's a remarkable site. And actually, the bull snake here, bull snakes are excellent diggers. Racers are terrible diggers. And so this bull snake is probably maintaining or improving the quality of this nesting site for the racer. Not on purpose, but for its own eggs. The racer's just taking advantage. And that's something about racers. They're real takers. They don't give much. The other problem, the problem with eggs, apart from just having to have the perfect conditions still, because you can't control the conditions once you've laid them, is eggs can't run away for the most part. Again, amphibians have some examples where they can. But eggs usually aren't very good at escaping from predators. So along with being sort of stuck where they were put, they are unable to defend themselves. So unless the parent stays with the eggs, which does happen in some reptiles and amphibians, there's not much security in laying your eggs. This is a painted turtle nest, and you can see by these little round dough balls, that means a hognose snake was here. And that hognose snake came, used its hoggy nose, and did just what a hog does, and dug up this nest perfectly, and it, I presume to leave insult, left only one egg in the nest. But this was the distinct predation event of a hognose snake. This is very classic for them. So there's a real risk of laying eggs. So when you only have a little bit of time to make a lot of babies, because we live in a very difficult place to be a reptile and amphibian, it might help if you can control the temperature for your developing embryos. And so a lot of our reptiles in Alberta are actually live bearing. There's variations on a theme with live bearing in terms of maternal provisioning, but in general, we'll say live bearing, still fed with a yolk, so lictrophic. Horned lizards are my favorite example because they're one of my favorite creatures. There's a baby horned lizard that has just been given, this mother has just given birth to that baby. She had between 6 and 13, based on average numbers for Alberta, of those babies inside of her. She started her summer when she was at like her healthiest at about 20 grams. By the time she was able to give birth the day before this baby was born, she was probably 40 grams, so she doubled her weight. That's an immense amount of investment, but what it allows her to do is make a lot of babies in only a couple of months. It's because she got pregnant in May and she gave birth at the beginning of August. So that's an immense amount of development to feed and process in such a short period of time. And then once the babies are out, they're on their own for the most part. They kind of stick around their mom sometimes, but that's a whole separate question. The other thing is, even if horned lizards don't necessarily defend their babies. An adult horned lizard, once the babies are out, the babies just run away. But you can also protect your babies by having them internally. So a garter snake, a gravid or pregnant garter snake, can slither away better than a bull snake that's left its eggs in a hole in the dirt. So that mother can escape keeping her baby safe and herself by keeping herself safe. But even after they're born, some reptiles and amphibians do help their babies stay safe. Rattlesnakes are a key example. They tend to give birth in communal rookeries in Alberta. So there'll be multiple females. So there's one female, there's another female, there's a third female. This site only has 3 females every second year. They only has 1 female every even year. But every time, once the babies are born, they hang out around their mother and the other adult females for a week or two until they've shed their skin and they can properly defend themselves a little bit better. And so their presence, and I'm not necessarily saying maternal care, but it's a version, even if it's by accident, of maternal care, because her presence means that any little bird's not going to come pecking around. The crow's not going to try and steal the babies necessarily because there's a large, dangerous adult female right there. Now, even though the eggs are quite different between amphibians and reptiles, and we've already discussed how they're different, the real observable difference between reptiles and amphibians is in that metamorphosis stage. And that's because the larvae of all of our reptiles and amphibians, or of all of our amphibians in Alberta, are aquatic. This is a long-toed salamander here. You can see it looks a bit like the adult. You might not be able to tell the species right first off if there's multiple species in the area, but it looks salamandery. It has some plumose gills that do define it from the adult. The adults are terrestrial. And it's more adapted for an aquatic situation. It's got a fin and a mouth that's built for sucking as opposed to biting. But the real novel ones for my money are the frogs. This is a spadefoot, a plain spadefoot tadpole, and these are chorus frog tadpoles from the same pond. They don't look anything like the adults of these species. If you were given an adult spadefoot and a tadpole, you would not necessarily know that those are the same species when you first look at them. And that's because these are weird little crazy fish-looking things, and a frog doesn't look anything like that. And that's because they have to undergo metamorphosis. So at a certain point in their life, their eyes will migrate, they'll lose their beak, because they have a beak when they're a tadpole, they'll lose their tail and they'll grow limbs. They also shorten their guts from the gut of a herbivore or a grazer to a carnivore's gut. So there's a whole bunch of things going on when you're a tadpole. In my opinion, it's hands down the most interesting thing about frogs is this tadpole stage, because there's all sorts of crazy ecology, crazy physiology, crazy morphology, and it's all ostensibly without the sexual selection elements that you have to deal with when dealing with adults. So it's like a whole other animal. It doesn't compete with the adults in any way. It's fantastic niche partitioning. But that development stage takes time, and not all of our amphibians have a lot of time. This is a spadefoot pond in southwestern Saskatchewan. You can see here, this is not a very long-lived pond. It fills up every year. It's an ancient bison wallow, and it's still maintained by cattle. This is a cow footprint with about 40 spadefoot tadpoles in it. But if you live in a place like, say, near the river in Edmonton, where you've got a nice big beaver pond and you have some time to metamorph, some of those species can take their time. But if you live in a spot like this, you have to get on your horse and go. And so these animals, spadefoots, actually can do it about as fast as any animal can metamorph. They go from egg to frog in only a couple of weeks. It's temperature dependent, but temperature's not a thing they lack. So they can go, and some of them even change their morphology to become cannibals, to get more protein to develop faster. So there's all sorts of little cues that they go on and all sorts of tricks that amphibians use to metamorph as quickly as possible. The opposite end of the spectrum is where you're living in a cold place, where it may take many years to get enough nutrition and process enough nutrition to get big enough to be an adult. And in some cases, it makes no sense to even become a terrestrial adult at all. So remember that salamander in the lightning storm before? This is the same species, but this one is from a oligotrophic lake in Kananaskis country. This is an adult, even though it's retained the neotenic form of a juvenile, except for it's gigantic. This one is 15 inches long. And so There's only a few places left where these animals do this. And in a lot of their range, especially along the mountain edges and in the mountains, they used to be the dominant vertebrate carnivore in a lot of these lakes. So this is a picture of the lake. There are no fish in this lake. Fish can't get up to some of these lakes. They're separated by waterfalls until people started introducing them into these lakes. And so most of these high mountain lakes used to be dominated by amphibians. They were the thing consuming most of the invertebrates and smaller vertebrates that lived in them. And this lake is one of the few places where that still happens. It's also very cool in that the rest of the community that comes to feed on this lake, so animals that would usually be eating fish like mergansers and grebes, are actually feeding on salamanders in these areas. So back to reptiles for a second, just to sort of suggest that even though there's less differences between juveniles and adults of reptiles than there are typically of amphibians, there's still enough difference to confuse identification. So this is a juvenile racer, yellow-bellied racer, eastern yellow-bellied racer, if I'm going to go with the full common name, and this is an adult. So you could see someone walking over this snake and panicking because maybe they think it's a rattlesnake because it's got all these blotches, or maybe they think it's a bull snake. And so we miss the identification. We don't see racers where we actually are seeing racers. But one thing that all the juvenile stages of reptiles, amphibians in Alberta, and pretty much across the world, do is they get eaten. They are ecological cannon fodder. There are so many of them, and so few make it to adulthood that they have all sorts of strategies to try and get through this, but most of them don't make it. This is a collection of western toads amassing near a pond edge to go and try and make it to the surrounding woods. So you've seen the sea turtle National Geographic type images of all the sea turtles emerging at once. It's actually used by lots of different organisms, including many of our reptiles and amphibians. Horned lizards also do something similar to this, where they all tend to give birth within about a week of each other. So all of a sudden, there's no baby horned lizards, and then you're covered in neonates. The hills are covered in neonates for a few weeks until the birds and the snakes whittle them back down. The next thing they do is hide really well. So I'm going to put this up for about 10, 15 seconds. If you can put your hand up when you see the lizard. It's a pretty big screen, so hopefully you can see it. It's about the size of sort of the medium to small rocks, just to give you some tips. So put your hand up if you see it. Okay? And I'll show you where it is in a second. All right, 5 more seconds. Okay, so it's right there. And this one actually moved, so it's even more visible than it was when we first scared it. This is why we just sort of walk through the habitat with sticks when we're looking for them. So yeah, you can see hiding is a really effective strategy for some of these species. And there's some reason to believe that horned lizards are actually fairly cryptic chemically too, so even dogs aren't better at finding them than humans, unless the dog's really well trained. So they can find the scat really well, but they actually don't tend to find the lizards better than a trained human observer. The other thing is just reminding everyone how scary you are. What harm can you pose to another potential predator? So rattlesnakes are our best go-to because they're our only medically significant venomous snake species in Alberta. But you can see it's an intimidating appearance. This big, hard S-coil, the rattle, the noise and the huffing and puffing that they make, it's an intimidating display. This is the exact same display. This tiger salamander is trying to tell me that it's got toxins in its tail, and if I go to chomp down on it, I'm going to get a mouthful of unpleasant taste. So these are both the same strategy, just slightly different outcomes for me. The other option is, if you don't pose a serious physical threat to your potential predators, pretend like you do. This prairie rattlesnake and this western hognose or plains hognose were found about 400 meters apart north of Medicine Hat. And you can see it's doing its best. It's a little less athletic than the prairie rattlesnake. It's a little less intimidating, but it's enough to make you just take a second look, which gives that animal a moment to hopefully get down into a burrow and escape. Another form of mimicry is auditory mimicry. And this is a juvenile bull snake. You can see here, above its tongue, at the edge of its windpipe, it has this epiglottal keel. This is where the group of bull snakes and gopher snakes gets their name, their generic name, Pictuophis. That means the phlegmy snakes. This thing rattles back and forth when the animal exhales really hard, and it actually makes a very convincing rattlesnake noise. And that's actually really common in areas where rattlesnakes are. In this area, baby burrowing owls also make a rattlesnake noise, and despite the fact I don't think they need any reason to be seen as scarier, badgers also make a pretty convincing rattlesnake noise. And then we get into some slightly weird defenses. Another case of the magnificent hognose snake and its acting prowess. Pretending to be a rattlesnake isn't its only trick. Some of the individuals you'll come across, if you come across enough of them, will actually play dead. And they're quite convincing until you try to flip them over, and then they'll flip right back over. So unlike a real dead snake, which flips over and stays flipped over because it's dead, these will really try and sell the fact that they are upside down, which means dead. The other one is shooting blood from their eyes. Now, some may ask, what is the benefit of shooting blood from your eyes? And that's a valid question. In greater shorthorn lizards, which is the species we have in Alberta, it's not a common occurrence, so much that we could ever test it yet. But in some closely related species, they actually shoot blood at the mouth of their predators. And usually only with dogs, so foxes, coyotes, domestic dogs. But for some reason, dogs hate the taste of lizard blood but love the taste of lizards. And so that's just to remind them that, like, oh, my blood tastes terrible. You wouldn't want this in your mouth. So yeah, there's not very many occasions where it's been seen in Canada. This is one example. I've never seen it personally. This was taken by my former boss, Dan Raffla. He was only in the park for 3 days when he saw this. I've been looking for 20 years to see it. I was so mad. But he let me use his picture. But despite all of their defenses, reptiles and amphibians are still, for the most part, not super high up on a trophic chain in Alberta. And they still tend to get eaten eventually. This is a great plains garter snake, Thermoregulation radix, serving as predator of a northern leopard frog, but also as prey for a Swainson's hawk here. And you'll often see Swainson's hawks with snakes, particularly garter snakes. Here's another trophic chain. I like this one because it's all species at risk. It's just species at risk eating other species at risk, which shows some of the tricky elements of doing species by species conservation. So this is a 9-spotted lady beetle that was eaten by a greater shorthorn lizard, which was eaten, or at least stabbed, by a loggerhead shrike. Many of the lizards we find killed by shrikes only have their livers missing or a couple of organs. They tend to be fairly wasteful. They just love stabbing so much. But I really enjoy that one. So this gets to how they find their prey. And there's a fair amount of work done on snake and reptile amphibian eyes. And for the most part, because we're binocular primates that stand well above ground and have good color vision and can see long distances, we say their eyesight's not very good, but their eyesight is often very, very, very applicable to what they do. If you're only this tall, how far do you have to see? Because you're going to run into something in the way anyways. So a lot of the eyesight is very applicable to the animal that's using it. And for things like leopard frogs that are quite excellent hunters, they seem to see just fine enough to cram food in their mouths. And these large diurnal snakes like racers and garter snakes have reasonably good eyesight because they actually use their eyes primarily that's their primary means of finding and capturing prey. This is a classic racer pose. This is called periscoping. This is what they do when they're looking for food. You can see, though, there's still a tongue. Another element of the optic system of snakes, and I'm going to talk a lot about snakes in this section because they're kind of the best studied for this type of stuff, is the loreal pits of rattlesnakes. Now, these are essentially like a chamber eye of a nautilus. They do attach back into the optic system of the snake. So they are, for as far as we know, very much act like a second set of eyes, but they're a very poorly receptive eye. They don't have the spatial resolution of a normal vertebrate eye, but they're extremely sensitive to temperature changes. So they can detect a temperature change of 0.003 degrees Celsius. So extremely sensitive, just poor spatial resolution, but they fit into the eye systems, so they can then use their eyes to help cue in and make that final strike. They also have these spectacular tongues. Everyone knows about snake tongues, and this has evolved on a number of occasions in squamata, or the lizards. And this bifurcation of the tongue allows them to see three-dimensional chemical trails. There's lots of amazing chemical signaling in amphibians that I don't know enough to really speak properly to, but chemical signaling in snakes is really interesting because that tongue doesn't actually do the chemical reception. It is a collector, and it does essentially what a greyhound does when it sniffs 2 times. It compares between the 2 points of sniffing and makes a gradient in its mind, right? The same way we do when we're looking for like barbecue. And when they put their tongue out, they get that in stereo at the same time. So that tongue gets drawn into the mouth. There's really no taste receptors on the tongue. There's only a couple taste receptors in a snake's mouth, and they're on the roof of the mouth. It then draws the tongue back in, and there's a couple papillae at the bottom of their jaw, in front of their tongue, which then get put up against the roof of their mouth, where an organ called the vomer nasal organ connects that chemical sensitivity to the brain. And that's paired, and then they see that in stereo. They have some version of a gradient. I don't know how they see it because that's outside of my ability to see. But it's a very cool system. It makes them fantastic trackers, or in the case of a rattlesnake, can help them see a trail that's used and which direction the animal might be coming from because they know one side's stronger. Yeah, here's another example of the tongue of a snake. I just forgot to advance the slide. This is a western terrestrial or wandering garter snake. So another one of our sort of badlandsy garter snakes, probably the one you guys find the most around here. Now, once they've found their prey, they have to retain, capture, consume their prey. And one way to do that is venom. And so the most famous venomous species in Alberta, of course, is the prairie rattlesnake. They are large, front-fanged, potent venom that you don't want to experience. Hognose snakes are also venomous, but it's a slightly different version of venom. It's a different gland it comes from. Again, all venom is some continuum of salivary gland exudates. So everything the salivary glands make, if they have an impact on the prey, you could make an argument that you could call it venom. In the case of hognose snakes, it's pretty clearly a venom. It's a special gland, the Duvernoy's gland, and it has a duct that ends right about here where you can see these 2 fangs. Unlike a rattlesnake, the fangs on a hognose snake are at the back of its mouth. And they're quite large, as you can see in this picture, but they don't tend to bite people as much. That's why I'm handling it in that fashion. But this one was actually the same one that was playing dead. This one was a fantastic actor. I would work with her again any day. But most of our reptiles and amphibians don't use venom or constriction like a bull snake uses constriction. They basically just grab things, overpower them, and swallow them. This is an unfortunate shrew that hopped in front of a leopard frog on the road one night when it was raining, and that was the end of the shrew. It is an ex-shrew. It's a former shrew. And the leopard frog will now have a good amount of time to process that. That's how all of our garter snakes and racers as well, they just sort of grab things and just swallow them. It's not pretty, but it's very effective. But once they've eaten all this food, they need to process it. So like that frog with the shrew in its belly, they need to find some way of getting enough heat for their enzymes to work correctly and hopefully process that food so that it doesn't go septic in their stomachs and kill them. And so this is probably our best thermoregulator in the province. I don't think I'm speaking out of school for that. But the horned lizards are one of our best thermoregulators in terms of accuracy of finding their body temperature. This one was sitting in a rock cluster that was 42 degrees on the ground temperature. I've seen them up to 64 degrees on ground temperature. So they live in a very hot environment. Heat's not their problem. Here is an example of horned lizard movements and the temperatures around them. The green line is the ground temperature in the sun. The red line is the ground temperature in the shade. And then the blue line is the ventral temperature of a lizard. So each lizard has 3 points, one for ground, one for sun, or one for sun, one for shade, and one for the lizard's belly. And you can see here, again, on the y-axis we have temperature, on the x-axis we have hour in the day. You can see in the early morning, they are in a big hurry to get warm because it's cold overnight in the semi-arid parts of Alberta and Saskatchewan. And that sun temperature comes up a little bit slower, but then really starts to go. And once they get a little too hot, I mean, we're going over the mid-30s here, they come back down and they start scuttling back and forth into the shade at this point. And then by the mid-afternoon, you can see the overlap between the confidence intervals here. They're pretty much exclusively in the shade in the mid-afternoon because it's plenty hot. They don't need to do anything else to stay warm enough. At that point, cooling off is a bigger problem. So they actually use the thermal inertia of large glacial erratics. They squish themselves up against the rocks, and they take the cold from the north side of the rock and try and transfer as much, or get as much, shed as much heat as they can into those big rocks. Our turtles have an additional problem in that water is seldom at their optimal temperature, but all their food is in the water. And so turtles have to make a real trade-off in terms of how often do they spend in the water gathering food versus up on the surface in a nice hot sunny spot digesting that food. Thankfully, all these animals are very energy efficient, so they can get away with it. But there's a larger trade-off here. And for the amphibians, there's even more of a trade-off. And that's because the amphibians can't really bask in the sun. Their skin's really not, for the most part, adapted to basking in the sun. And so most amphibians in Alberta are nocturnal to some degree, and almost all of them are thermoconformers. That is to say, they don't spend a ton of time actively basking. They kind of just are the same temperature as the environment around them. And a good portion of ours can't handle the daytime, so many of them, like this little spadefoot, this is a plain spadefoot here, spend their days buried in the sand. And in fact, many of our reptiles and amphibians for the winter, which is a condition that none of our species can survive on the surface, have to go underground at some point. This leads to really interesting aggregations because these sites, like the nesting sites, are often limiting. There's not that many sites that they can provide an access to a snake the size of a large adult rattlesnake, subsurface conditions where it's not going to get too cold for them. So when they find that site, they all kind of group up there. So in Alberta, we find lots of aggregations of multiple species with multiple age classes, all occupying these areas. This site, this one's in Saskatchewan, at one point had more than 250 rattlesnakes that lived in it. It collapsed in 2011 due to a really fast thaw, but it formed new sites and the snakes have been rebuilding. This is since 2011. So another interesting overwintering or brumation story is the painted turtle, which lives again in the Milk River. This might be the toughest animal I can think of. Not only do they have to bask during the sun and feed in cold water, so that constant shock of temperature changes for their body, but in the winter they go down to the bottom of a pond or a slow-flowing river and they just stay there for the next 6 to 8 months. So they will not breathe for the next 6 to 8 months, which is pretty impressive. Some reptiles, some turtles, do have the ability to extract some level of oxygen from their surrounding environment. Painted turtles are not one of them. There is no oxygen exchange for a painted turtle, so they bury themselves right in the mud to try and avoid freezing, which makes them the most northern turtle in North America. But now they are dealing with the fact that their metabolism is all anaerobic. So anyone that has run, 5 kilometers, 10 kilometers, a good long run where you're into your anaerobic metabolism, you're going to get a cramp, right? That cramp is lactic acidosis, that lactic acid building up in your muscles. If you're on an anaerobic metabolism, you are building up acid. These turtles aren't breathing for 6 months. That's a lot of acid to build up. So, thankfully, their metabolism decreases with temperature. That's what brumation means. It's different from hibernation in the sense that it's not an active state that they put themselves in. It's just a decline in their metabolism. But these guys also sequester calcium carbonate from their shell because it's a great source of bone. They sequester calcium carbonate from their shell and they use that to buffer the acid in their blood. They still survive a pH drop of 1, like from 7 to 6. So they can still survive a whole logarithmic difference in pH. So they're remarkable animals. That's like pouring vinegar into your blood. Absolutely stunning animal. Other animals have, I personally don't think it's quite as amazing as being able to survive acid blood, but some animals can freeze solid. In and of its own right, basically they make themselves dead for 6 months. I think that's also pretty amazing. Wood frogs, this is a wood frog from Wood Buffalo National Park, are famous for this. They basically take glycogen and make a cryoprotectant in their livers and then put it throughout their blood so that they don't burst their cells when they freeze. And we've suggested, Larry Powell has suggested, that horned lizards are doing something similar. And some of my early stages of my work are confirming Larry's observations. We found lizards going down to minus 10 degrees Celsius. So presumably they're freezing. But once all that awful time is up, then it's time to get back to business of making more reptiles and amphibians. And one of the first things we hear every year is frogs. Leopard frogs are relatively early breeders. They usually wait for the rivers to flood and then breed in the flooding pools. They have the cool dual vocal sacs that come out over their shoulders. A very neat vocal sac. Spadefoots wait until it's a little bit warmer and they wait for the thunderstorms of early summer, and then they breed in rain-filled pools. So there's different ways of doing it, but they both have spectacular vocal sacs. They usually call from cover. They usually call floating in the middle of a pool. And these guys you can hear from a quarter mile away easily. These are a little bit quieter. Some animals get right to business right out of hibernation or brumation. These are red-sided garter snakes from Wood Buffalo National Park. It was 2 degrees Celsius when I took this picture. This is the coldest I've ever seen a snake out. And they were actively courting this female. So this is the female here, the big one. And then these are 3 males that are sort of wrestling each other / trying to court the female at the same time. Others wait until a slightly more pleasant time of the year to try. Once they've had some food and they've had a drink and everything's a little calmer, then they try the wooing game. This is a pair of rattlesnakes mating. Rattlesnakes mate in the midsummer, but that leads to a problem because then you've got sperm and egg meeting right as winter comes because our seasons are so short. So what rattlesnakes do is they actually save the sperm and then delay fertilization until the next spring. And so this, along with the sheer investment of having so many large babies, means that rattlesnakes usually only breed every 2 years. And once that's done, then you're back to more babies. And that's kind of where we started the life history story. So I'm going to end it there. And if anyone has any questions, I'd be happy to take them. If anyone has any comments, I will also accept constructive criticism, but constructive, please.